Good morning, everyone. Hi, my name is Xiaosong Ma from Qatar Computing Research Institute. So today we'll be talking about our research that we did some I/O characterization automatically with DDN switches. So we are familiar with high HPC centers parallel I/O setup, right? So this one is one typical thing you see, which is the Spider file systems architecture at Oak Ridge National Lab. And this is for their Spider file system, although the machine is now like a little bit old, ranking currently number 9 in the world. Still, this is the representative architecture. We have the supercomputers, compute nodes at one side, connect together with their interconnection network. At the other side, we have the storage network, which contains a lot of storage servers running Lustre. So they're OSS, object storage servers, and then these storage servers are connected via DDN switches to the RAID groups. Okay? So most people see this architecture, but at the same time, not many of us are aware that these switches themselves are actually doing their own monitoring work. So for some time after the system was installed, actually all these monitors, the switches themselves are collecting their I/O bandwidth for every second granularity for both read and write, and the data were collected from via a monitoring tool and stored in a relational database. But just people didn't do anything about them. So this is what the data could look like. Okay, so for a period of time, this is the entire Spider system's read performance. Once every second, you get the combined traffic from each switch, and you can put them together. This shows you how much read activity is going on in the production system. Okay, so this provides us with coarse granular logging capability. What's good about that? So this logging itself has almost zero overhead. You don't have to do anything. It has no impact on user applications I/O or computation. And finally, users don't have to modify their code or compiler, or you don't have to modify the operating system either. What's bad about it though is that here we are seeing things at the switch level, and we are looking at combined traffic. So all the I/O traffic from the different applications running together are mixed together. How do we get some sense out of it? How do we understand what the applications are doing and try to optimize them in any way? So this brings us to one prior work we did, which was also published at the FAST 2014 conference. Okay, so we looked at these mixed logs, but then we think that by putting them together with the job log, we can figure out the I/O intensive applications use patterns. Okay, the idea is that most applications keep doing the same thing again and again, and with the job log, we can find out exactly what time an application has executed its job, starting from when and finishes at what time. By intercepting the aggregate I/O logs together with the job logs, we can find out that, for example, for this application, 3 times it executed in history, carve out that 3 pieces of aggregate I/O and put them together. So the intuition here is that if an application is I/O intensive, right? So the common things, the common activities we have identified from these 3 pieces of history data belong to this application, while the differences belong to the background noise, which come from the different applications that happen to be running together with them. So with this idea, we performed the signal processing and the data mining tricks and end up finding out the I/O signature of an application. So at what time it will be doing periodic I/O and how much read or write traffic it will generate during each I/O burst. But then there is a strong assumption here, meaning that we require all the jobs to be exactly the same, which is not the case. Sometimes we can run an application for 20 time steps, sometimes we run for 2,000 time steps. We could also have executions where we don't turn on I/O at all, right? So our follow-up work was published at Supercomputing 2016 solved this problem by relaxing the rules and still finding out what the applications are doing. And then given that information, we did IO-aware scheduling. So basically you can look at the applications, figure out how IO intensive they are, and then based on their potential contention for IO resources, delay one of them or both of them, etc., so that we get overall better performance. Okay, I'm not going to give details, but then just a quick summary of results. So we looked at 5 months of logs from the Titan production system, which gives us, almost 200,000 jobs belonging to 10,000 unique applications. And with no prior knowledge of these applications at all, we did our automatic identification based on the DDN switch data and find out potentially 42 of them are IO intensive. And we need to get ground truth from them, right? So we identified from these 42, only 16 belonging to Oak Ridge National Lab. Because this is joint work with them, we feel comfortable of contacting these users. So we emailed these 16 applications owners, and exactly half of them replied. So we got 8 applications, which give us their actual IO characteristics, and we compare them with what we have guessed just by the very coarse granular server level logs, and our results are highly accurate. Okay. But then there was one thing puzzles us from this whole study, right? Our tool works, but from this study you can see out of all these jobs, 10,000 unique applications, only 42 of them are identified by our system as IO intensive. For the others, they are doing very low bandwidth, low IOPS thing that we couldn't even see from the log. So what is going on, right? So we have found out, which also confirms prior study, that users are not using IO resources well. We buy these expensive systems which has high bandwidth, high IOPS, high metadata handling capability, but a lot of times users are just doing IO in a very inefficient way. And what is worse, what we have identified from our recent monitoring on another supercomputer, the current number 3, Taihu Light in OLCF, we have found out that sometimes users use disruptive IO modes, for example, end-to-end mode or end-to-one mode, where you have millions of cores writing to one single shared file or one separate file by themselves. So these IO modes not only produce super low bandwidth performance for your own application, they turn out to be very disruptive to everybody else. So not only you don't get good performance, you generate enough IO intention to bring down everybody else. So that is the one thing we need to solve. We need to have system software that can provide better, transparent IO optimization, doing better, just not horrible IO modes, and have better user education. So that's it. I hope you find it useful. Thank you.